There's a star so large that if you swapped it for our Sun, its surface would swallow Mercury, Venus, Earth, Mars, Jupiter, and keep going, all the way out to the orbit of Saturn. Our entire planet would be buried somewhere deep inside it, lost in the glow. It's called Stephenson 2-18, the largest star we've ever found. And its size is almost the least strange thing about it. This is a star that's mostly empty space, that shouldn't be able to exist by our own rules, and that we can't even be certain is really the biggest at all. Just how big are we talking? The numbers stop making sense almost immediately. Stephenson 2-18 is about 2,100 times the width of the Sun. Light would take nearly 9 hours just to travel once around this star. The fastest aircraft humans ever built would need more than 1,000 years to lap it. In terms of sheer volume, you could pour 10 billion suns inside it. It's about 20,000 light years away, in a small, faint constellation called Scuti, the Shield. You'd expect something 10 billion times the volume of the Sun to be unimaginably heavy. Well, it isn't. Stephenson 2-18 holds only around 15 times the Sun's mass. 15, not 10 billion. All that volume, almost none of the substance. Spread that little material across that much space and the result is close to nothing at all. The outer layers of the star are thinner than the best vacuum we can create in a laboratory on Earth. Emptier than the near vacuum at the very edge of our own atmosphere. The largest star we know of is, for the most part, a glowing ghost. If you could somehow fly a probe toward it, you wouldn't smack into a surface. You just drift into gas that very gradually got thicker, with no clear moment where you could say, now I'm inside the star. A star that enormous and that empty runs into a problem. By our own physics, it arguably shouldn't be able to exist. Stars have limits. When astronomers model how large a red supergiant, a dying swollen star like this one, could possibly get, the theoretical ceiling lands somewhere around 1,500 times the Sun's radius. Past that, a star should become so unstable that it sheds its outer layers faster than it could hold onto them. Stephenson 2-18's estimated size is around 2,100 solar radii, well beyond the line theory says is possible. So either our models of how big stars can get are incomplete, or there's something we're getting wrong about this particular star. Part of why it's so swollen is that it's dying. It's burned through the hydrogen in its core and is now fusing heavier elements, which makes a star like this balloon outward into a bloated giant in the final chapter of its life. It's also flinging enormous amounts of material out into space as it goes. The vast size isn't a sign of strength. It's a star coming apart at the seams. And the bigger one of these stars grows, the more precarious it becomes. The sheer flood of light pouring out of its core pushes outward against gravity, and near the upper size limit, that radiation pressure starts to win, lifting the outer layers right off the star. A hypergiant the size of Stephenson 2-18 is balanced on the very edge of blowing itself apart. But before we crown it the undisputed champion, there's an awkward truth about these record-breaking giants. The record keeps collapsing. For years, the title of largest known star belonged to one called Scuti, measured at around 1,700 times the Sun's radius. Then, the Gaia spacecraft pinned down its distance far more precisely, and the whole estimate fell apart. With the corrected distance, Scuti's radius dropped to just 755 solar radii, less than half its supposed size. Gone overnight, simply because we finally measured how far away it really was. Another famous giant, Canis Majoris, was cut down the same way, from over 2,000 solar radii to around 1,400. And the pattern is always the same. The measured size of a distant star is only as good as our distance to it. And distance is one of the hardest things in all of astronomy to pin down. Get the distance wrong by a third, and the star's radius comes out wrong by a third as well. And Stephenson 2-18 itself rests on shaky ground. Its size estimate ranges anywhere from 1900 to 2400 solar radii, depending on the method. There's even real doubt about whether it truly belongs to the star cluster it's named after. And if it sits at a different distance than we assume, every one of these numbers changes. On top of that, the star pulses, brightening and dimming, which means its actual size is shifting over time. We've crowned a champion we can barely measure, in a contest where the leader keeps getting demoted. So how do you measure a star you can't even see as more than a single dot of light? Very, very indirectly. You can't point a telescope at Stephenson 2-18 and see a disk. From 20,000 light years away, it's a single point of light. So, astronomers work backwards. They measure exactly how much energy the star pours out and how hot its surface is from the colors in its light, and then use a law of physics that ties brightness, temperature, and size together to calculate how big it must be. The cluster it lives in was first catalogued in 1990 by American astronomer Charles Bruce Stephenson, and the headline size came from a study of these red supergiants in 2012. That indirect method is also why its edge is so slippery. With an atmosphere this thin and this far flung, there's no crisp boundary where the star stops and space begins. Just a slow fade. Defining how big it is means choosing where in that fog you decide to draw the line. For an object this strange, even the simple question, where does it end, doesn't have a clean answer. Two astronomers, using two perfectly reasonable definitions of the edge, can walk away with genuinely different sizes for the very same star. All of which leads to a bigger question. Is there a limit to how large a star can be? Stephenson 2-18 and its fellow hypergiants seem to be pressing right up against it, possibly even past it. And they're strange in another way. Despite being the largest stars known, they're relatively cool, glowing a deep red at around half the sun's surface temperature. Yet, because their surface area is so colossal, Stephenson 2-18 still shines with the light of nearly 500,000 suns. It's worth being clear about what the largest means here though. These red hypergiants are the widest stars, but not the heaviest. The most massive stars known cram well over 100 times the sun's mass into a far smaller, hotter, blue-white ball. Stephenson 2-18 wins on sheer size, not weight, which is exactly why it can be so vast and so empty at the same time. What we don't know is whether it will keep its crown. A better distance, a sharper model, a closer look, any of them could shrink it tomorrow, the way Gaia shrank UI Scuti. Or it could turn out to be even larger than we think. What is almost certain is its ending. As a dying, unstable giant, Stephenson 2-18 will eventually collapse and erupt as a supernova, scattering itself across that corner of the galaxy. So the largest star we've ever found is a contradiction wrapped in a record. It's big enough to swallow our entire planetary system, yet emptier than laboratory vacuum. It's larger than our own physics says it should be able to get, and it sits at the top of a list whose rankings collapse every time we look more closely. Stephenson 2-18 isn't just a big star. It's a reminder of how much we're still guessing at, even about the most enormous things in the sky. This channel is about exactly these moments, when something we thought was a simple fact turns out to be stranger and shakier than it looks. If that's your kind of thing, subscribe. And if this one was worth your time, a like genuinely helps the channel grow. Thanks for watching. Clear skies.